Anybody remember that from GChem? We were talking about equilibrium. All right, so let's chat Liège principle. So the more, when you add in the mag sulfate, the more water that gets absorbed by mag sulfate, the faster the forward reaction goes to produce more water to keep up. It's like you're trying to keep up with the loss of water on the other side. So if you take again, carboxylic acid and a primary or secondary amine in the presence of some type of drying agent like mag sulfate, all right, you're going to get an amide. And again, I want you to work through the mechanism for this because it follows the same or similar mechanism to ester formation. Let me put that in here. We've talked about that. All right, so it follows that same type of mechanism where your amine is going to attack your carboxylic acid, and then eventually you'll do a proton transfer and lose water. All right, so I want to focus in now on the second reaction, which is amine formation. And this is also, sometimes you'll see this referred to as Schiff's base synthesis. Have y'all done this in our lab where you made a Schiff's base from a chalcone and an amine? Anybody remember?
No, we haven't.
Y'all haven't done that in 323 with Dr.
I don't think so.
Okay. That used to be one of the labs that we did when we made like chalcones and then take the chalcone and derivatize it, turn it into a Schiff's base, but I'm not sure what he's doing at this point, but that's all right. So anyway, the reagents for Schiff's base synthesis, you need an amine, a primary amine, right, and an aldehyde or ketone. All right. So when we take that aldehyde, let's show that mechanism for that. All right, so let's take that aldehyde that we had, and we're going to react that with what's on here. So it's an R group. I just put a methyl group on here. All right. So all of these carbonyl reactions have something in common. All right. Again, I can't repeat this enough. Anytime you add in a nucleophile to a carbonyl, and the amine can be a nucleophile or a base, but anytime you add a nucleophile in to a carbonyl, it's going to attack at the carbonyl carbon because of the dipole. Let's got a dipole here, so this is going to attack like that, and you're going to break the carbon-oxygen pi bond. What type of intermediate do I get when I attack a carbonyl?
An illite?
No, not an illite. That's a different reaction. Think back to when we first started talking about esters and how to make them, right? Remember we said anytime you attack a carbonyl with a nucleophile, you get a tetrahedral intermediate. Right, so for the aldehyde, it's going to look like this. That's negative, and I'm going to put the amine up here. Right, so this is my tetrahedral intermediate. Any carbonyl addition reaction is going to go through that. All right. Now, the goal, one of the goals is to lose water. How can I turn this oxygen right here into a water molecule using only what I have. And this is positive. I'm sorry, I put the charge on there. Using only what I have. How can I turn that into water?
Proton transfer
How many times am I going to have to do that?
twice.
Okay, great. Excellent. Do I have 2 protons that are present
Yes.
right on that nitrogen, right? So I can steal one of those real quick, like so. Give that back. And that's going to get me to another intermediate, which looks like this. O H. And then now this is all right. So you do that first proton transfer to get here. And then can I do another one? Do I have another hydrogen that I can pull off?
Yes.
I do, right? I can just do that again. And this mechanism, it seems long, but it's really, once you get past the initial addition part, it's just really proton transfer, right? 2 proton transfers, and then it's one other step after that. All right, so boom, I'm going to pull off that proton, leave those electrons with nitrogen. So I'm going to come here. I have this intermediate now. What do we call this when you have a water molecule present as a leaving group? What's that? What do we call that? That water molecule. Anybody remember?
Hydride.
It's a hydronium ion. All right. Now we home free almost. We need to get rid of water. And this is something we talked about the other day. How can I force water out? What can I do?
Elimination.
An elimination. Excellent. How can I do it? Without the aid of anything external. I got everything I need right here.
It involves the nitrogen.
Yes. Because let's go back to the product. You see in the product, right? One of the main product is here. And you see that there's a double bond between nitrogen and carbon, right? So I need to go down here and figure out how I can do that. All I need to do is put a pair of electrons here. Like that. Is that right?
Yes.
And then I can force out water at the same time. So through elimination, I can force water out and I can get my carbon nitrogen pi bond that I'm trying to make. Right? What do we call that when a neighboring atom can supply electrons like that to force out a leaving group? It's one of the last things we talked about on Wednesday. This neighboring group participation. Then we talked about that Wednesday, right before we left, when we were doing the acetal, the hemiacetal.
Yes.
This Friday. Is that right? We talked about that right here. Is that right? All right. So now that's my amine. Right, or we call again a shift space. So with the amine, there's another analog of this. It's not on the handout, but we're going to talk about it since we're here and we got time. If I use, and this is with a primary amine, all right, if I use a secondary amine, I actually get what's called an enamine, and we're going to go through the mechanism for that too. Right. So the enamine, let's think about that. The first term is derived from the suffix "ene," which means there's going to be an alkene present. And then the second term is where it is, there's a nitrogen. Right. So let's take the same aldehyde here, plus, in this case, I'm going to use a secondary amine. So I'm going to do this. Right, so the secondary amine it just has 2 alkyl groups attached to it. Primary amine only has 1 alkyl group attached. Tertiary amine will have 3 alkyl groups attached. Right, it follows the same bond order as carbon. So what am I going to do first? The amine is going to act as a nucleophile. The carbonyl is going to act as an electrophile. You look at all these reactions, it's all stuff from part 1. Nucleophiles and electrophiles and functional groups. Right? What I found out over the years teaching this section is that the struggle is not in the remembering the reactions, it's the functional groups and not knowing what specific functional groups are. And if that's the case, then that's the issue, right? Because if you don't know what the functional groups are, then you don't have no way of knowing how they're going to react. All right, so let's look at that. What's going to happen first? Is anything different going to happen? Different stuff that we've already been looking at? No, it's the same. It's going to be the same type of mechanism. Attack the carbonyl first, right? Get to a tetrahedral intermediate. And from that tetrahedral intermediate, that's how you figure out what's next. If you can get the first step to get to the intermediate, then you can look at the intermediate and kind of think about what happens next. It's not about remembering all of the steps all at once. It's one step at a time. So let's see what we get from that. We're going to get a tetrahedral intermediate that looks like this. So this is N. I'm going to put the H up here. And this is positive. All right, now what? Think about the mechanism we just did. And think about the fact that we still want to lose water, okay? That's still one of our goals, is to lose water as a leaving group. So what will I do next?
Proton transfer.
Proton transfer, just like in the mechanism we just looked at. All right, so I'm gonna take this proton right here, and I'm gonna give that pair of electrons back to nitrogen. This is acid-base chemistry from Organic 1. It's not groundbreaking, earth-shattering new stuff. All right, so now I'm at this intermediate. All right. Now I need to lose water, but there's no more protons on the amine. All right. Do I have a proton? Do I have any protons somewhere else that I can take off? can't touch this one. If this is what you're thinking.
Can you use one from the methyl?
That's a good point, but the answer to that question is no. The methyl protons, I'm glad you said that. That's really a good observation, because you do have protons here, but they're not acidic enough. There's a proton that's more acidic than those, and that would be these alpha protons right here. Right, remember I said the part of the name, the ene, meant that there'll be an alkene present. So those alpha protons are going to allow me to put a double bond here and lose water at the same time. All right, so let's see how we can do that. So first, let's do the proton transfer. And I'll write that over here. So there are no protons left on my amine. So we'll use the alpha protons. Right, and remember, alpha is just the protons that are on the carbon adjacent to where your functional group is. So I'm going to do a proton transfer. I don't want to draw this. It's going to be ugly, but we'll take it. We'll take that pair of electrons right there, and then let me fix this. Right, and then that pair of electrons I'm putting here on the carbon. Like that. Right, so I'm going to make a carbon anion at that site. So then my intermediate is going to look like this, right? Here I have a hydronium. And then that carbon now has a negative charge on it. Right, so it's this carbon right here that's negative, the alpha carbon. Now, what can I do to get rid of water?
NPG.
Mm-hmm. NGP. But I know what you're saying though. We can take these, put them here. Let me change the color of that. Put them here like that and lose water. So now my enamine looks like this. So this is H still, this is N with two methyl groups on it. And I have a double bond here. So you can see the ene part is right here. And the amine part is here. So we call it an enamine. Right? Any questions about that one? It's a little bit more involved than the shift base, but not much. It's just a one extra. Actually, it's not even an extra step. It's just that your second proton transfer happens at a different site. Right? So we see that this is a proton transfer. This is stuff that we've already seen before. This is also a proton transfer. Right, and then this is elimination. All right, using neighboring group proton. I mean, neighboring group electrons. Who was that gave the answer?
Panetta.
All right, good, excellent. All right, questions about these two? Anything about it? The mechanism looks like a lot, but it's really not. It's really not. If you understand the first step, you can figure out how to get through the rest of the reaction. All right, we got one more amine reaction that we're going to look at, and that's here. and this is a synthesis of amines. Should have done that first, but that's okay. Can't crop it. That's fine. So this is Gabriel synthesis, right? It is a way to synthesize primary and secondary amines. That's what it make primary and secondary amines. And it's easy to spot because the reagents are very specific, right? You need phthalate. This is actually where your nitrogen is going to come from. You can see that there's a nitrogen right here, right? This is my nitrogen source. And then you need an alpha halide. All right, there's going to be a substitution reaction that happens, the SN2 type substitution that happens. And we'll talk about that when we get to the mechanism. All right, and then you need a base. The base is there on purpose, is to make phthalate more nucleophilic, which we'll see, and then you need water to pop open the ring. So let's look at it. So the first step in this reaction is proton transfer between the base and phthalate. So I'm just going to use the OH. That's KOH. So this is just simple acid-base chemistry, right? Even though the phthalate is more, the proton on the amine is usually not acidic, but the fact that it's that those two carbonyl groups are there, it makes it more acidic because you can stabilize the conjugate base by resonance. All right, so that's that. So we end up here. That's negative. And then again, you can stabilize that nitrogen, the charge on nitrogen by resonance with those two carbonyl groups. So that's that plus water. And then the potassium is just going to hang out wherever the negative charge is. Anytime you have a counter ion like potassium, sodium, lithium, that counter ion is going to find a negative charge. It doesn't matter what atom it's on. All right, so that's that. So now let's just do CH3 methyl iodide. This is so in the second step, this is where, so phthalate is, you do proton transfer, let's just say to activate. Phthalate. And then in the second step is SN2 type substitution, right, with your alpha halide. Right. So this is something that we've seen before. We talked about for a whole week about substitution, right? So this is just going to attack here. Let me draw that out. I'm gonna get my life together eventually. This is gonna attack here, kick off iodine. So now you have an alkyl group on your amine, or on your nitrogen. So that's that. Right, so now you have that plus Ki, right? Because again, when iodine leaves, it's going to be negative, and whatever the counter ion is, it's going to follow it, right? So it's going to find whatever's negative and just hang with that. You'll have an ionic attraction with that. So now you just need to pop the ring open, right? And that's the purpose of the water, right? And this happens twice. It has to happen twice because you have to basically hydrolyze that nitrogen off. So we're going to attack here and then here. And I'm going to show one step, and then from that you can get the gist of what happens in the second hydrolysis. Right, so now you have this hydronium, right? And again, we can do a proton transfer. Let me change the color of that arrow, make it more apparent. We can do a proton transfer here, right? And this looks like a lot, but it's not as bad as it looks. This is positive. And then like that, pop that open like so, and you end up with a carboxylic acid here, and then the amine here, or the amide here. Right, and then you'll just do the same thing again to release the amine, right? So you'll add another water molecule in, like so, and then you'll go through the exact same thing. All right. Any questions about and again, the goal of that synthesis is to generate amines, right? So this is a way to make amines, just like we talked about ways to make esters, ways to make amides, ways to make alcohols and things like that. This is a way to synthesize amines, pretty efficient way too, from phthalimate and an alkyl halide, right? In the presence of a strong base. Any questions about that, about the Gabriel synthesis? And you can do this with a primary alkyl halide or a secondary alkyl halide. Right, primary or secondary. And that'll give you either a primary amine or a secondary amine. All right, questions, any questions? All right, let's jump down. We got 12 minutes left, so let's start working through some of these examples. And I want to start with this reaction wheel right here. And we're going to just predict the products of each reaction. Let's start here. Right here. This is at 6 o'clock. So what we're looking at now, we got these reagents, we have this starting material. And the question is, what type of reaction is that, where you take an alcohol and you react it with a base followed by an alkyl halide? What is that going to give us? This is my starting material. What type of reaction is that?
Oh, it.
Okay, the base and the alkyl halide do match the acidic condition, but there's one thing missing that distinguishes this from acidic. And it was two things missing. One, there's no triphenylphosphine. And then the other thing that's missing is that there's no carbonyl. Right? Remember, acidic is a way to turn carbonyls into alkenes. These conditions right here are for Williamson ether synthesis. Right, so if I take that alcohol and treat it with sodium hydroxide and then add in, I'm just going to abbreviate that, add in methyl bromide, right? It's a way to make an ether, because it's that CH3 group from the alkyl halide that's going to end up bonded to my alcohol. Right, this was one of the first reactions we talked about. So again, my suggestion is to make some flashcards with the reagents and the start materials and the products and the outcome, right? And then if you have room on the back, you can put a mechanism, but that's going to be the best way to remember what the reagents do. All right, let's go to 3 o'clock. This is another one that we should, it's not that bad. So you got potassium permanganate, which is a superoxidant in the presence of a primary, and this is, let me get this clear too. For many of these reactions, we're looking at the alcohol as the functional group that's going to react. There's only one that doesn't react with the alcohol, and this, we haven't touched it yet. So with this, it's the alcohol that's the functional group that's reacting. So I got that, potassium permanganate. What am I going to get from that? Potassium.
Carboxylic acid.
Say that again.
A carboxylic acid.
Carboxylic acid, excellent. Right? So my product is going to look like, don't steal it. So this is pH. Like that. And then my alcohol is actually going to get oxidized up to a carboxylic acid. Right, that's what potassium permanganate does. It oxidizes primary alcohols up to carboxylic acids. It doesn't stop, right? Remember, we talked about the alcohol oxidation. The potassium permanganate won't stop at the aldehyde state. It'll keep going until it has oxidized the carbon all the way up to the acid state. All right, now what if I take the acid and react it with an alcohol? Let me give you some other conditions. And I heat it up. What do you think?
Transesterification.
Great. It's a transesterification. What is it going to do? What am I swapping out? It is an esterification, and it's going to be an addition followed by an elimination, just like the majority of these carbonyl reactions are. So what am I swapping out here? Right, it's this alkoxy part of your alcohol. That's going to swap out with the hydroxyl group here. Even if you don't know the mechanism, you should be able to predict the product based on the reagents. If you take a carboxylic acid and heat it up with an alcohol, any alcohol, you're going to get an ester. Right. And if you look up here, it kind of gives you the reactions that are available. Excuse me. All right. Let's go to here at 9 o'clock. What happens when I take and again, we're looking at the alcohol. What happens when I take a primary alcohol and react it in the presence of chromic acid?
You get an aldehyde.
Excellent. This is also an oxidation. Right, and it's going to take that primary alcohol up to the aldehyde. So this is the aldehyde that's going to come from this alcohol right here. All right. Now there's another reaction waiting for that aldehyde, right? So this would be like if I were to write this out as a sequential synthesis, this would be 1, and then this would be 2. The second step in the synthesis, not the mechanism. I don't get that confused. All right, if I'm synthesizing something, that means I'm trying to make it. So this will be the second step in the synthesis. What type of reaction is that? And what is going to happen to the aldehyde?
This is the Vidian.
And you can tell that because you have all the ingredients. I hate to say ingredients because it's not like cooking, but you got all the reagents. You got potassium hydroxide, which is your base. And remember when we first started talking about the Vidic, I told you what to look for. You got a strong base, you got triphenylphosphine, you also have an alkyl halide. What do all these things do when you put them together? The base, the alkyl halide, and the triphenylphosphine.
You get an alkene.
Yes, in the product. But before we react this stuff with the aldehyde, what do we get?
An illet.
Yeah. All right, so this proceeds through an illet, a phosphonium illet. All right, so then how do I predict the product of that? I gave you a little method the other day, and let's see if we can, if you remember what we talked about. So without going through the arrow pushing, and because all that stuff is down here in the handout, we're gonna go through arrow pushing, mechanisms, all that stuff. But how do I get to the product? I don't have to show the steps. What did I tell you the other day that you could do to know exactly what the product is going to look like? Because you know, first of all, the product has to be an alkene, right? Because it's a Vidic reaction, and that turns aldehydes or ketones into alkenes. So you go from a carbonyl to an alkene in the product. All right, so what alkene, what is the alkene going to look like? What's the shortcut I gave you?
You swap the oxygen with whatever is attached to the bromine minus the bromine and the hydrogen.
Okay, good. So this is, and this is a common mistake, and this is why I'm saying this. you have to find wherever that halogen is. So this is the bromine here, and it's bonded to a CH2. Right? So this is the carbon right here that's involved in replacing oxygen. And I said that if you subtract it out, I get in a rudimentary sense, you can't do this in real life, but just a way to think about it. If I take out a HBr, I'm going to be left with CH3, right? And that carbon is the carbon that's going to be in my alkene. So when I take that and I take what's so now I'm going to put this carbon right here. CH3. It's always the carbon that's attached to your halogen or your alkyl halide that replaces oxygen. Always. So that's a quick and dirty way to think about that. Is to find the carbon in the alkyl halide that's connected to the halogen, pluck off a hydrogen from it, take the halogen off, and what's left, put that where oxygen is in that carbonyl and take oxygen out. All right. Any questions about that? We'll talk about the other reaction when we come back on Monday. Can y'all believe Monday, Wednesday, Friday, and we're done? It's crazy. So what I need you to do, because it's like super quiet, I need you to make sure that, oh, go ahead, Cornetta.
For the reaction we just did, the